So, last chapter before the big fat guy with a red suit comes. Or I could say the last one of the year. Big one. Big one. Kind of to your advantage. You don't have to know a whole lot prior to this. Normal distributions stuff. But this one, guys, this one is like one that takes care of all next semester. Like if you don't understand what a sampling distribution is and what they do and how they act, it's going to be tough. So it's not that difficult. It just takes some effort to understand them, okay? I'll be doing a lot more talking than probably you will be doing writing. That's okay. Just, again, we'll make sure you write down the important things. But like I said, really just focus in on the process of what we were doing here, okay? So far in this course, just make sure we kind of put a little cap on what we did. The very first thing we did this year was collecting the data, okay? Collecting the data. Chapter 4, it's the only time we look at it. Analyzing the data, looking at it. What does it tell us? The different types of graphs. We did univariate with 1, 2, and 3. I'm sorry, that was chapters 1 and 2. This is old information. Then chapter 3 was the bivariate data. That's the chapter test that I still have not put in yet. I will get that done within the next 2 days, okay? And then we did probabilities, chapters 5 and chapter 6, the chances of things happening, okay? And you have to understand that in order to do what we're getting ready to do. So this is the portion of stats that's going to put all this stuff together, all the collecting, the probability, and the looking at the pictures, okay? Statistical inference. And that's, again, that's what we're doing rest of this semester. There's 4 major topics of statistics: collecting, analyzing, probability, and then drawing conclusions. And that's the inference part of it, okay? Drawing conclusions from the sample. We're going to be talking about sampling distributions. Please try to focus in, lock in, because I'm telling you, this is, if you don't get this, it's going to make next semester miserable for you. Miserable. We haven't focused a whole lot on notation. Notation from now on is going to be very, very important. Notation is very, very, very important. If you put the wrong notation, you're going to get dinged. And if you don't put notation, you're going to get dinged. Up until now, it's kind of been a little bit here or there, okay? Population. This is something we talked about. This is probably day 1, but I want to make sure we understand population is everything we're interested in, every individual we are interested in, the entire group. You all know what the population is. It's not new to you. But again, it's something that you got to start understanding. What is the population of interest? That very well could be a question. What is the population of interest? So you have to look and see what the sample came from. If the sample came from BHS seniors, then my population of interest is all BHS seniors. But if my sample came from BHS students, now it's all BHS students. So you have to understand what the population is and what we're inferring to, the inference part of it. What are we inferring to? Okay? And then, of course, the sample is just a part of that population. Again, that is nothing new to you guys. This is not that foreign. It's just something we want to make sure we kind of start getting our head wrapped around. What are we talking about? We're talking about the population, we're talking about the sample. Most of the time we're talking about the sample, but we're talking about, or we want to know what the population does, or how it acts, or what is the value. Okay, but a lot of times we use the sample to do that, to infer it with. A parameter, we decided this, I think this was in chapter 2, maybe chapter 1. That is a number that describes that population. It may have an average, it may have a range, it may have a standard deviation, but all of that, whatever that number is a parameter. Okay? A lot of times we don't know what those values are because we don't know what the information about the population is. That's why we do statistics. We do statistics for samples to infer to that population. So a lot of times we don't know what those values are. But that's that number that describes it, okay? And then, of course, a statistic is the number that describes a sample. That can have a center, that can have a mean, that can have a median, it can have a mode, it can have a standard deviation, it can have a range, it can have a median, range, IQR, right? So each one of these have same values, just statistics are different than parameters. Statistics go with samples, parameters go with populations. So again, they may say, what is the population of interest or what is the parameter? If they're asking for the parameter, they're looking for a number. If they're asking for a statistic, they're looking for a number. Okay? All right, again, all that's not new. That's all repeat stuff. This is not new, but it's things that we got to start talking about, right? So the sample mean, guys, we use X bar for the sample mean. If it's a sample and we're looking for the average, we're going to use X bar. X bar. Anytime you see an X bar, we are talking about the sample and the average, right? If you guys are my population and I pull a sample out of you guys and find out how many or what the average of your test score was, then that's X bar because that's a part of it. Whereas if we're talking about the population, we're using the Greek letter mu, the fancy looking U looking, whatever you want to call it, right? X bar, mu. A lot of times we don't know what that is, but we might assume what it is, or they may tell us what we think it is. We got to separate those. You got to separate those. Don't put an X bar for the population. Don't put mu for a sample. Okay? It's just big key type deal. It's not, most of the time we don't mess that up, but I just want us to make sure we're focused on those things. Standard, this one we haven't done. So we talked at one time about numerical data, which is what this is. Categorical data deals with proportions. You're either in that category or you're not in that category. So if it's a sample, they're going to use P, and we'll just call it P hat, kind of like Y hat. What percentage of you guys have A's? That's P hat. Okay, that's just this, that's a sample. Whereas in the population, they will use just a P, just a plain old P. It's actually a Greek letter rho. Actually, they use pi, but it's hard to write pi equals 0.42 or 46. It's hard for me to write that because I'm a mathematical nerd. So X bar P hat mu, and they'll just write P for that. So if it's the population proportion, it's P. It's P. Then we have the sample standard deviation, S sub X. You don't have to put the S sub X. You don't have to put the sub X. We just kind of get in the habit of doing that. And then the population, of course, is the Greek letter. P hat, X bar, mu, P. Those 6 things, guys, you've got to know. And typically they have a number after that. Equals. So those are the variables or the values or the notation that we got to use. If we're talking about sample, we're talking about X bar, P hat, or S sub X. In population, we're using Greek letters, mu, rho, sigma. Any one of those, okay? Questions? Feel good? All right. This one's an easy question right here. Identify the population, the parameter, the sample, and the statistics. So they're asking for 4 things. So really, I'm just making sure you guys understand that there are 4 things that they could ask for. Population of interest is the values. Parameter is the number. The sample is the value or the words, I guess. And the statistic is the number. The Gallup poll asked 515 randomly selected U.S. adults if they believe in ghosts. Of the response, 160 said yes. 160 said yes. So the population, U.S. adults, all U.S. adults. I don't know what the parameter is. Whoops, parameter. Percent of all who believe in ghosts. I don't know what that number is. They didn't give me that number. Sample 515 adults. Statistic. This one I did get. P hat equals 160 out of 515. You think there's nothing hard of that? Yes? Any question about that? So distinguish between the population and parameter. They didn't give me a parameter this time. A lot of times they don't. A lot of times they don't know what it is. Sample, statistic. Good enough with all that? P hat, because it was a categorical data. You either believe in a ghost or you don't believe in a ghost. So it's not necessarily numerical data, it's categorical. You're either in that category or you're not in that category. And so that's why it was P hat, it wasn't X bar. We don't have an average. It's just 160 said yes out of that many. That's a little new to you guys. That will start becoming a lot easier for you. Population, all U.S. adults, parameter, the proportion who believe in ghosts, sample, the 515 who were interviewed, and the statistic is P hat, 160 out of 150 or 515. You can turn that to a decimal if you want to. All right, a couple of homework questions on that. Easy, easy, easy. But again, it's a big, big deal. Many students lose credits on exams when defining parameters because their description refers to samples instead of populations, or because the description isn't clear about which group of individuals the parameter is describing. So please, when you define a parameter, suggest using the words all or true. Notice when I said all U.S. adults, I think that's what I even said. All U.S. adults. Just always try to use that word all or true in your description to make it clear that you aren't referring to a sample. All right, beautiful. Statistics goes with samples. Parameters goes with populations. If they ask for a parameter, they're talking about the population. If they're asking for a statistic, they're talking about the sample. Okay, beautiful, beautiful, beautiful. Here's where I'm going to skip a couple of slides. I don't know what your notes go to. So skip a couple and go to sampling variability. Sampling variability. Okay, let's talk for just a little bit. So here I got you 28 kids, right? Young adults, not really kids anymore, right? So 28 of you guys in here. I'm going to put all of your names into a hat and randomly select 4. Okay with that? Out of those 4, you got a test score on the last test, whatever it was. And between those 4, I can put those 4 together, add up those 4 and divide by 4, and I would get the average of those 4 test scores. Okay with that? That would be an X bar. Let's just say 82. That's the average of those 4 test scores. Okay with that? Now, I put all those names into that, and I pull out 4. Will I pull out the same 4? Probably not. I might. Probably not. I'll get another X bar. Is it going to be 82? Probably not. Could it be 82? Could be. Could it be the same? Could be. So let's say that this time it's not. It's 84. Good enough with that, right? Throw all the names back into a hat, pull out another 4. I'll get another X bar. I'll get another X bar. I could do that so many times. And the more times I do that, the more idea I'm going to have what the overall average is. Fair enough with all that stuff? Okay, well, here's sampling variability. Here's what it says. And this is like really, really common sense. Sampling variability. Different samples of the same size from the same population produce different numbers. Duh. I mean, that's really, really common sense, but that's a word that a lot of students just think, oh, sampling variability, but exactly what does that mean? Different samples of the same size from the same population produce different values, different statistics. Because each one of those was an X bar. That's a statistic. And I could do that over and over and over again, but I don't know how many times I need to do that, but I could. Sometimes they'll produce the same, and sometimes they'll produce different. They could be all over the place, but it kind of depends on which 4 I got. Y'all okay with that? Sampling variability, different samples of the same size. All of you were size 4 from the same population. You guys were all of you guys were the population, produce different values. Duh. I mean, it's really, really common sense, but that's what sampling variability is. Sampling variability. Different samples vary. They vary. They have different results. They could have the same results. They could. But they also could have different results. I would think it would be weird to have a result of 99 and 24. I would think that would be weird. Possible, but weird. This is what this whole topic's about right here. Okay? So, sampling distribution. Y'all okay with those different X bars I got, right? 84, 86, 72, 91, whatever I'm going to get, right? I'm going to do that, and I'm 4 and 4 and 4. And if I put all those on a stinking number line, and we've done this before in class before, a couple times, what was that one? The frog tail, right? We made a dot plot of that frog tail, and I could put all these dots on a number line. Okay? All of them sample size 4. And I could just keep doing this and keep doing this and keep doing this. Eventually, I'll have a picture of all these things. So we're talking about sampling. That's chapter 4. And now we're talking about looking at the data. That's chapters 1 and chapters 2. Now we're analyzing it. Now we're going to talk about the probability, right? My guess is this thing will start having a lot of dots like closer together, like closer to the true value. It'll have very few averages that are up here like 100. I don't think I have 4 of them that got 100, but I don't think I have 4 that's going to get me down to the 30 range either. Okay, with all that kind of stuff, I'm probably going to center it around some value. Well, here's what sampling distribution says. It's the distribution of values taken from that statistic, whatever that statistic is, X bars, P hats, of all possible samples. That's what the key is. All possible samples of the same size from the same population. All possible samples. I don't think I have time to do all possible samples. All possible samples. Again, soak that up. That's what's huge. If you can start understanding this, guys, it's big. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. There is 28 of you guys in here. And I'm selecting samples of 4. So if I'm throwing all of your names into a hat and I'm taking a random sample of 4, it's very, very possible I got 4 right there. It could be those 4 cats right there, and I'll get the average of those 4 tests. Y'all okay with that? And then I'm going to put everybody's name into a hat again. I don't think I'm going to get all 4 of those. But if I'm going to get sampling variability, I got to get all 3 of those with every single one of you guys. And then I got to get the other 3 with every single one of you guys. And I got to get the last 3 with every single one of you guys. And I'm still not even close to all possible samples. Y'all with me on all that? There's going to be a whole bunch of these X bars, a whole lot of them, a whole lot of them. That's what the sampling distribution is. Now, are we ever going to do that? No. We have to know how this acts. What is that going to look like? And if you know what that looks like, we're going to take what? One sample. We're going to take one sample and think, if I know what this looks like, how does that one sample fit with it? Does it fit with something we expect to see or something we don't expect to see? Now that's the probability part of it. And if it's something we expect to see, then we're not going to dispute it. We're not going to say it's a bad sample. We're not going to say that it's disagreeing with the population or anything else. However, it's something we don't expect to see. Now that's where we start having our issues. This will make a little bit more sense next semester. But this part you have to understand. All possible samples of the same size from the same population. So you're going to have a bunch of these X bars. A bunch. I could calculate that, but I don't want to. Yay? Okay? Okay, soak that up. Soak that up. That's what this whole section's about. Unbiased estimator. I don't know what this... I still don't understand this. If the mean of the sampling distribution is equal to the parameter. We're just going to learn it. We're going to go ahead. It makes sense. I just can't quite explain it. Let me rephrase that. I can't explain when this doesn't happen. When the mean of the sampling distribution. Okay, let's soak all this up again. Now, the sampling distribution, that's all these stupid X bars. All those X bars. All of them. I'm going to take the average, look at my notation here, the average of all those X bars. That's all of them. So that's a population. That's all the X bars. I'm going to find that value. Okay with that? If the average, if all these X bars are different than the population, or I should say the same, it's unbiased. If it's different, then it's biased. If it's different, then it's a biased estimator. So unbiased. If the mean of the sampling distribution equals, it's unbiased. If it doesn't equal, then it has to be biased because it's a bad sample or we did something weird or something's wrong because it's biased, right? Bias means it differs from the truth. It differs from the truth. Not that big of a deal. This is a big deal. That's a big deal. And if you understand this, you kind of understand this, but if you understand this, you do understand that. Okay, y'all soaked in, got what you got. Okay. You can do. Go. You got a definition for this? Yeah, put it down. This you already know, I think, but I don't know how well I've emphasized it this year. Variability. That's the spread. That's the spread. Variability of the distribution. It will decrease when I increase the sample size. Write it down and let me explain to you so that it makes sense. Variability of the distribution decreases when the sample size increases. Here, let's just do it this way. Let's go here, here. No, let's just do this. Let's go back. Okay. I got all these X bars. This was a sample of size 4. It's possible, well, I say it's possible, I don't know for sure. But let's say that 4 of you cats got 100 on the test. 4 of you guys. Okay with that? It's possible to have, a dot right there at 100 because the average of those 4 would be 100. So I'm going to increase the sample size, not 4 anymore. Now I'm going to say 8. 8. I still could get an 84. I still could get an 86. I don't think I'm going to get a 100 because I don't think there were 8 100s. So because of that, I no longer have a dot way out here at 100. That's got to bring these dots in. I don't think I'm going to have an average of 30 because I don't think there were 8 of you cats that got a 30. There may be 1 or 2, there may be 4 or 5, but I don't think there's 8. So I don't think it's possible to do that. It's going to bring those dots in. It's going to decrease that variability as I've increased the sample size. Kind of makes sense, yes? So that's what I'm saying by that. As you increase your sample size, that variability has to decrease because something weird doesn't have as much weight. If there's 120 out of a sample of 3, that has a big weight on it. But if there's 120 out of a sample of 8, it doesn't have as much weight. Okay, here we go. Let's see if any of this makes sense. To determine how much homework time students will get in class, Miss Lynn has a student select a random sample of 20 chips from a large bag. So picture this. I got a large bag up here, and some student's going to select 20 chips out of that large bag. Okay? The number of red chips determines the number of minutes in class you're going to get to do your homework. I'm going to tell you, or Miss Lynn tells there's class, there are 200 chips in the bag. There's 200 in the bag. You're getting 20 of them. 100 of them are red. So the other 100 are not red. So 50% are red. Jenna selected a random sample of 20 chips. Okay, so now, because you guys understand a little bit of probability, we know that there are 200 chips in the bag, and 100 of them are red. Jenna, or the student, is selecting 20. How many red chips should she get? 10. Are we going to be surprised if she got 10, 9, 11? I'll be surprised if she got 0. Be surprised if all 20 are red. Kind of okay with that, right? Without looking, she got 7 red. That's kind of on the verge of being a little surprised, but maybe not too bad. Does this provide convincing evidence that less than half of the chips are red? So we kind of have to figure out the chances of this kind of stuff. It's bringing the probability in, but bear with me. Here we go. First question is, what evidence that less than half are red? Okay, so here's what I'm going to write. P equals 0.5. That's what she's telling me the population is. Okay with that? I got a p hat of 7 out of 20. Which is less than 0.5. I don't know what 7 out of 20 is. Point what? 2 goes into 7, 3? 3.5? Again, notice my notation. The population is saying that 50% are red. The sample was 35%. These are not the same. We're expecting them not to be the same because of sampling variability. However, there's some evidence that there's not because what? 0.35 is less than 0.5. That's giving me some evidence that it's not half and half. Any question about that? Some evidence. Because my sample doesn't match the population. That's some evidence. Jenna's sample proportion was 0.35, which is less than 0.5. That gives me some evidence. Is that giving me enough evidence? No, because of what? Sampling variability. I might get 7. Provide 2 explanations for getting the evidence for part A. There's 2 reasons why I got the evidence of part A. What was that evidence? 7 out of 20. What are 2 explanations for why it's not 10? Bad sample, or I shouldn't say bad sample, just a sample, sampling variability, or she's lying. It's not half. One of those two has to happen. Either a bad sample, which we have to probably think that, or she's lying. It's not half and half. Those are the only two explanations you got. Kind of keep that in mind, again, next semester more times than not. Okay? It's possible that Miss Lim is telling the truth and Jenna got a p-hat less than 0.5 because of sampling variability. It's also possible that Miss Lynn is lying and less than half of the bag is not red. We use technology to simulate 500 SRSs of size 20. We've done this several times in class. Well, we haven't done it, but we've read about this several times in class. From a population of 200 chips, assuming 100 of them are red and 100 are blue. The dot plot shows the p-hat of the sample proportion of the red chips of those 500 samples. So here's my 500, right? 100, 100, 50, 50. Here's one p-hat. P-hat was 8 out of 20. Here's another p-hat, 11 out of 20. I simulated that, 500 times, and that's what the dot plot looks like. In fact, the dot plot looks so close, you can't tell them they're dots. Here's 0.5. Notice it's the highest. What'd they get? 0.35. That's right here. That looks like it's possible. Okay with all that stuff? Good. What does each dot represent? A simulation of 20 chips. And how many of them are red, or the proportion of red chips out of 20. Okay with that? Now here's what I want to ask you. Is that a sampling distribution? Think. You don't have to answer. Is that a sampling distribution? So this is the difference. That is not a sampling distribution. That is a distribution of samples. How many? 500, I think. It's not all of them. It's not all possible. That's just 500 of them. Y'all okay with what I'm... So there's a difference between a distribution of samples and the sampling distribution. What if I did another 500? I'd still have a distribution of samples. I'll just have 1,000 of them, not the sampling distribution. Like, I don't know if I'd ever have time to do all of them. Yay? Okay. Click. The population distribution is here. The distribution of a sample, another sample, and that is 500 of those samples. Distribution of sample data. Nope, 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 nope. I've already talked about all that. I've talked about all that. I've talked about that. I've talked about that. I don't know how much of this is in chapter or in 7.1. Okay, so I skipped a lot of stuff on your notes, but I think we're okay. I'm going with this. It's worked really well so far this year. I don't know how much of this is 7.1, but I don't want you to get a question and not be there. Miss Lynn, if you guys remember that question right there, Miss Lynn told me that 100 of the chips are red. That's her claim. I'm telling you, 100 of the chips are red. We have to believe that to be true. We have to believe that's true. Why? We don't have any other thing to go off of. We have to believe the claim is true. Coca-Cola sells 12-ounce cans. 12-ounce cans. We have to believe what? There's 12 ounces in that can. We have to believe that. Is there? I don't know. In order to believe or in order to test that, I got to do what? Get a sample. Find out how much Coke is in that one can. Find out how much is in another can. I can't just do one. We got to do several, right? And I'll find that sample, the X bar, and I'll see how close that is. If it's 12, I can't dispute it. I can't dispute it. If it's 11, I might can dispute that. She claimed it was 50%. I got a sample of 0.35. I can dispute it. I don't know if it's true or not, but it's not looking good. I may have just gotten a bad sample, though. I used to do all this. Just soak this up. I don't want to do it again. I think this is pennies made prior to 1980. Pennies are done now. We don't even have pennies. Before 1982 were made of 95% copper. Because of copper content, these pennies are worth actually 0.023 cents. You can find some of those. Pennies made after 82 are only 2.5% copper. Jenna once reads online that 13.2 of all pennies. So we have a P, 13.2% are before 1982. All pennies, there's 13% of them. That means what? 13 out of every 100 pennies are pre-1982. Jenna has a large container of these pennies. She selects a sample of 50 of them. She finds it 11, so I have a P hat. 11 out of the 50. Does that dispute or help verify this? Well, I have 11 out of 50, I don't think is quite 13%, so it disputes it a little bit, but I don't know if it's enough dispute. Just kind of follow along, y'all good? From the container finds that. Does this provide convincing evidence that the proportion of pennies that are pre-1982 is greater than that? Oh, that must be bigger than 0.382, whatever. This is really all stuff we're getting ready to do next semester. So I'm just kind of, they have some claim. We have to believe it's true. We're going to get a sample. We're going to compare that sample to that claim. Oh, they want you to identify the population, the parameter, and the sample statistic. Okay, which I kind of did that as I'm going. The population is all pennies, all pennies, all pennies, not pennies pre-1982. It's all pennies. The parameter is the percentage of pennies pre-1982, which happened to be 13.2. P equals, that's the population parameter. It equals to 13.2 because that's what they told me. The sample is the 50 pennies out of her bag, whatever it was, her collection. That was a sample. And then the P hat was 11 out of that 50. Several of you guys are writing something down. Who has a question about that? That's all I really wanted to talk about, that part of it. Parameter, sample, comparing, they're different. Do we expect them to be different? Yeah, I'd be more surprised if they were exactly the same. I'd be more surprised if they were the same. Okay. Sampling distributions, sampling distributions, sampling distributions, distribution of samples. Does Jenna have some evidence that more than? I think she did. Provide two explanations for this. Well, because she may have had a weird sample. So all her pennies might be old. Depends on how long her collection is, right? I have a bag of pennies up there that I haven't put a penny in and I don't know how long. So I guarantee it, I don't have any new pennies in there. That's what? This is a distribution of samples. I promise you it's not the sampling distribution. We use technology to simulate taking in 100 SRSs from size 50 from the population in which 13.2 was true. Amazing. 13.2 is the highest one. It's amazing how that happens. There were some times where we had more than 13.2. I guess all these. Less than 13.2. I forgot what her sample was, but it would be something we would expect to see or not. Again, those are things that we've done throughout the year already. Do we expect to see it or not? I don't expect to see this. I don't expect to see these. I don't expect to see these. Getting close. No, getting close. Okay with all that stuff? At some point, we'll say more than getting close. We'll put numbers to that. We have done that a little bit. Is that a sampling distribution? No, that was a distribution of samples. Is there, oh, there's one dot, oh, hers was 22%. 22%, one dot right there. Explain what that means. That was a simulation where 22% of the pennies were pre or post, I think post 1982. One sample whereas post 1982. Based on your previous answers, is there convincing evidence that more than? Explain your reasoning. Is it something we expect to see or something we don't expect to see? If we expect to see it, I can't dispute it. If I don't expect to see it, I can dispute it. If I expect to see it, if we expect to see, I cannot dispute it. I can't dispute it. Like any one of these, there's no way for me to dispute it because I expect to see it. Those happen so many times. Something way out here, that's what I don't expect to see. I don't expect to see that. I don't expect to see this. I don't expect to see those. If I don't expect to see it, then I can dispute that claim. If I expect to see it, I can't. Again, this is something that's just, it takes a little bit of a while to start getting this part. Okay. Terminology matters. Another big tip that I want to make sure you guys get that a lot of students miss points because they mess up. Never say the distribution. Don't just say a distribution without talking about the distribution of. Of. What are you talking about a distribution? Are you talking about the sampling distribution? Are you talking about a distribution of samples? Are you talking about a distribution? Okay? Being careful to distinguish a distribution of the population, a distribution of sample data, and a distribution of statistics. Just be very careful. Explain what you're talking about. Likewise, don't use ambiguous terms like a sample distribution. We're not too sure what that is. It could refer to a distribution of samples. It could refer to the sampling distribution. You will lose credit for misusing statistical terms. Don't. If you're scared that you are, you're better off not saying something. You follow what I'm saying, right? I've mentioned that several times. You're better off not putting something than putting something wrong. Putting something wrong, it's obvious. That's wrong. Not putting something, that may or may not be wrong. We talked about this at one time. Accurate and precise. Try to get away from this word here. If I get a sample of 4, that's precise. I'm going to get that average. That's right. That's accurate. I'm sorry. That's accurate. How precise is that is how close it is to the population. Precise and accurate. Increasing the sample size will not make it more accurate. It can't. It doesn't make it more accurate. It makes it more precise because you've narrowed it down. So be careful about that. That's a very, very common uh-oh. We talked about it in chapters 4 even. Okay. You guys are my test run. I skipped a lot of stuff, but I think I got enough to get through this lesson. We're going to start putting math to it on 7.2 and 7.3. But I think you can distinguish between the parameter and statistic. You could have done that before today. Create the sampling distribution using all possible samples from a small population. Now, guys, they're going to give you a small population. You can do a sampling distribution from that. What I mean by that is if there's just 4 of you guys and I want to take a random sample of 2, I can do that. I can't take a 4 from all of you guys. So you'll be able to have to create a sampling distribution from all possible samples of the same size. Use the sampling distribution to evaluate a claim. Okay, so that sampling distribution, evaluate that claim. Do we believe it to be true or not? We're going to have some evidence. Do we have enough evidence? And that's where that 5% is that we've talked about several times in this class. If we see it 5% of the time, we believe it. If we don't, okay? Distinguish among the distribution of the population, the distribution of the sample, and the sampling distribution. And hopefully your homework will help you decide on those 3 things. Okay? Distribution of a population, the distribution of a sample, and the sampling distribution. Those are three different things. Determine if a statistic is an unbiased estimator of that. If it's equal, it's unbiased. If they're different, then it's biased. And describe the relationship between sample size and the variability of a statistic. As that sample size increases, that variability decreases. I did, like I said, I skipped through a lot of that stuff, but I hope I didn't skip through enough that you can't do your homework. Focus in on those answers. This is one of those guys, I'm not going to necessarily focus in on which one's right, maybe why the other ones are wrong. You'll kind of follow what I'm saying on that, right? Don't always focus in on which one's right. Maybe focus in on why those other ones are wrong too. That'll help you for this lesson. This lesson also, if you get real bad, go to the book. They put all kinds of examples in there. Open up Achieve. You got this thing called a book. It's there. You don't have two of them. You only have one. But this is our book. It's about this time I got to start saying it because some of you guys need more help or you want more help or whatever. Unit 1, Unit 2. This is Unit 5 because it's Chapter 7. Sampling distributions. That's your book. Gives you an introduction, 7.1, 7.2, 7.3, chapter wrap-up, free response. There's the Frappy. There's the review. There's the review exercises. There's the Chapter 7 practice test. They give you all kinds of things. Cumulative AP practice test. Cumulative. Got a semester coming up in, ladies. Okay. I think it's posted. What time is it? 9:20. Yeah, is it posted? Y'all see it? Yes? No? Yes? Yes. I heard a yes and I heard a no. You see it? Homeworks? Beautiful. I missed you guys. You got it now? Beautiful. Beautiful. Man, I love this chapter. The what? The chapter 4. 3. 3.